All right, hello? Yep, I can hear myself. Okay. All right, start whenever, or you guys gonna? Okay, cool. Okay. All right. Well, good afternoon. Thanks for making it. My name is Audie Lee. I'm talking today about simpler volume encryption using Tang. I noticed a few of you guys were from the previous workshop, and when I was there, I talked that there was a simpler way of doing things than we currently do, and I think this is probably the way that things will go eventually. So let's check it out. To start with, let's talk about how volume encryption is currently implemented in OpenStack. So to start with, when we want to get an encrypted volume, we go to Cinder, and we asked it to generate a key. It then talks through Castellan to Barbican, or whatever your key manager is, and that generates a key, sends back a UUID to Cinder, and that's stored inside its metadata. And then, of course, when we want to load up the volume, we go to Castellan, we get the reference from the metadata from Cinder, send that UUID to Barbican, go through Castellan, bring the key over there. A few things we have to think about over here. So first of all, you need to store some metadata inside Cinder. Secondly, you need to securely store your key, so that means using a key manager that possibly has an HSM at the back end over here. So this is something that needs to be secure. Thirdly, you've got to transfer that key securely from Barbican over to Nova, so you need to have TLS connections or something like that that allows you to do that, which means more setup, whether it be certificates or whatever the case may be. So it's a fairly complicated thing. And it's made even more complicated if you want to try and think about doing something like bring your own key. So when bring your own key, you have your own key inside a key manager on premise, with the idea being that you don't necessarily trust your OpenStack administrator, and so you don't want to store the key necessarily inside the cloud. Well, how do you do that there? There have been two models that have been described here. One's called the push model and one's called the pull model. Right? In the pull model, what you have is you have a Barbican, and Barbican stores a reference to the secret in its back end there, so it doesn't actually store the secret. The pro of this is that in order to make this happen, you only need to change one component, which is Barbican. And you just need to enhance Barbican to go ahead and collect and get the key from your on-premise HSM. The disadvantage, though, is that Barbican then needs to have the credentials to go and get the key, and you need to be able to, again, set up TLS and the secure connection between your key manager and Barbican so it can retrieve the key. Okay. The second option is called the push model. And in the push model, when you create the encrypted volume through Horizon or UI of some sort, you actually provide that key. Okay. Now, the advantage of this is that the key is not stored permanently in the cloud anymore. So that's a good thing. The disadvantage, though, is that there are a whole slew of changes that are needed to Cinder, Nova, Horizon, maybe others, to basically be able to retrieve that key and then pass it along between the different services. You have to be able to pass it securely, so you need to have encryption and you need to have TLS between the various services, which is also not a bad idea. But you absolutely need to have that there. And you're still relying on the services to dispose of the key when the key is done. And then, of course, what about non-interactive flows, right? Because at that point, you don't have the key, so how do you boot up your server automatically when it goes down? So that's actually a question which I want to turn to now. Nathaniel McCallum, at one point, has been wrestling for a while on how to actually automate this. So if you have a data center, and one of the servers goes down in the data center, and it happens to have a root volume, which is encrypted, first thing that comes up, this password, right? And so you have to have monitoring software that lets you know that a particular server has gone down, and then you go to that server and you type in the password and everything's good, right? Except that it's a data center, right? So there's a lot of them, right? And if your data center has an outage at 2 a.m. on Christmas morning, things are a little more complicated, right? And so to try and get around this problem, Nathaniel McCallum and Bob Relyea came up with something called the McCallum-Relyea Key Exchange. Now, this looks pretty complicated, but it's actually not that complicated. I'm going to go through it a little bit. Basically, there are two steps. There's a provisioning step, and there's a recovery step. In the provisioning step, the server actually generates a public-private key pair. right? And that public-private key here, so this is the private key, and this is the public key over here. Okay? What it's going to do then is it's going to advertise its public key. The client's going to do the same thing. It's going to create a public-private key here. And if you had a standard Diffie-Hellman type of exchange, what would happen is that the client would then publish its public key over there, and both the server and the client could generate this symmetric key called K, which it would use as a shared secret, and that's how you set up the Diffie-Hellman exchange. Okay. The difference in this case, though, is that it doesn't publish its public key. Instead, it creates K, and it uses K as the key encryption key for your volume. Okay, and it stores that in a LUX slot. Okay, and then it retains a couple of things here. It puts also inside the LUX header, it puts the location of the Tang server, but then it discards K and it discards C. Right, so it's discarding its own private key, and it's discarding K. Now, at this point, you should be thinking, huh, how does that work? Right? Because at this point, if you were to reboot this server over here, this server would have no idea how to decrypt its own volume. Okay? All the information that is needed is lost. And that's where the magic of the recovery phase occurs. In the recovery phase, what you have is that the client creates a brand new public-private key pair, adds it over here to its public key, sends it off to the server acts on it, and from what it gets back, it can actually rederive K. So what that means is that the client itself can rederive that key encryption key, but only in the presence of the server, and the server itself cannot do anything over there. Now this is really cool, and I won't go through all the math, but it's actually quite straightforward. I'll be happy to do it afterwards if you want to. But here's the key points here. First of all, the client cannot decrypt itself. It can only decrypt itself in the presence of the Tang server. Okay? Secondly, no key material is ever transferred over. So that means that no other server, the key is never transferred anywhere. In fact, anything that is transferred over is either public or is of no use to an attacker. So therefore, anything that is between the server and the client does not have to be encrypted. No more TLS. Okay? Finally, because the Tang server is completely stateless, doesn't have to do very much other than do small operations, it's very small, very fast, can do thousands of operations per second, can scale very easily. So, network-bound encryption was useful because what you do is you have a data center, and you have a trusted network, and inside that trusted network, all of your servers can contact the Tang server and can then do the disk operations over there. How do you do that in OpenStack? Well, one way to do that is to use something like VPN as a service. So we're using VPN as a service inside this a diagram over here. You have a Tang service, which is on premises. Yeah. It appears to be a local node over here to all of your VMs inside your tenant. And therefore, if you then provision your volumes with that Tang server, they cannot decrypt unless that Tang server is available. So we now have a simple volume encryption that requires only the volumes and the Tang server, no other services, no key escrow, and transparently, we have bring your own key. There's a couple of features that we're going to need from Tang in order to make this really useful to us. The first is that we need to have the ability to blacklist specific volumes. Because right now, if your Tang server is no longer there, then all of the volumes you encrypted with the Tang server are not available, right? And you want to be able to maybe blacklist 1 or 2 volumes rather than all of them. And the second thing is we need to be able to do non-root volumes. The ability to do non-root volumes is actually something that's coming up in the next release of Tang, which will be in RHEL 7.5. So there isn't time, I didn't think there was going to be time to demo this. But I did do a proof of concept of this, and in the proof of concept, I use a Nova server to start up some instances which had been provisioned with a local Tang server. When the Tang server was there, everything was good. When the Tang server wasn't, you couldn't decrypt anything. Okay? The details are at this note over here. There's also some links towards Tang and Clevis and some documentation there. And finally, this is a link to a talk where Nathaniel actually goes into detail about the Tang protocol and everything that's involved in there. And that is it. So thank you. Any questions? No? Yeah?
Does the Tang system have to be outside of OpenStack? Or
it does not have to be outside of OpenStack. It could be in OpenStack. Right? If you did it outside, then you'd bring your own key. Right? If you didn't, you could put it on a VM that's in your local system there, and you could use that. Right? And that would be a simple way of doing volume encryption, but all within OpenStack.
How would you handle regions?
So, well, you'd have to have a Tang server available, right? Right? It doesn't decrypt unless the Tang server is available. So as long as you have some sort of Tang service available somehow, you get to it, you can get to that there. So that's something we'd have to think about if you'd have to have multiple different Tang servers available depending on what region you're in. But that could be something.
Can you replicate the yes keys of the process?
Absolutely, right. So the only thing that the Tang server needs is its own key. It needs the public-private key. That's the only thing it really needs is the public-private key of the Tang server. That's the only important part, really. So that's easy enough to replicate, and then you could put it behind an Apache server or something like that for load balancing or all that kind of stuff. But yeah, that's all that's needed. There's also something within Tang to be able to rotate keys after a certain amount of time. So it'll have an old key and a new key, and it'll have do that kind of stuff as well too. So. The Tang server has to be encrypted. Well, the Tang server has. I mean, the thing that's important there is that you have a public key private key pair, right? That's the only thing that the Tang server really needs, right? But that's it there. It never, just like any other private key, it never leaves where it's supposed to be. Right, it never leaves that server. So yes, but that server should be secured. Right. Okay. I am out of time according to that. So if there are any other questions, feel free to ask me. Okay. Thanks.